We're very happy to have Yufei Zhao come speak to us about popular common differences. So take it away.
All right, thanks, Sean. It's great to be here. Thanks for the invitation. So today I have the great pleasure of presenting some recent joint works with Jacob Fox at Stanford. The Hui fam is a PhD student at Stanford, so is David Stoner. And Ashwin Shah and Mehtab Soni both just finished their undergrads at MIT and will be staying on MIT to continue their PhD. Let's start with Roth's theorem. So this is one of the main theorems in additive combinatorics. Tells us that for a fixed alpha, O sufficiently large n, every subset of the interval from 1 through n with density at least alpha contains a three-term arithmetic progression. Okay, so there's a lot of work done on Roth's theorem, and in particular, a lot of attention is on quantitative bounds. How large does this n have to be in Roth's theorem? So in fact, we'll see a talk later this week by Sean that gives the latest improvement on quantitative aspects of Roth's theorem. Today, I want to explore Roth's theorem in a different direction. Note that a somewhat easy situation is if you take a random subset of z mod nz, or 1 through n, but z mod nz is slightly easier to discuss, with density alpha, then typically you expect the density of three-term arithmetic progressions to be around alpha cubed, just from a simple probabilistic argument. On the other hand, there exist sets A with density at least alpha, whose 3AP density is much less than random. So this is super polynomially smaller as a function of alpha. So the random is by far not the worst case in terms of the number of 3APs. There are constructions that give you much fewer 3APs. I won't go into the specifics of this construction, but it's essentially some blow up of a familiar example due to Behrend on large sets without 3APs. Actually, Behrend's construction will come up many times in this talk. Nevertheless, one can find, actually somewhat surprisingly, if you haven't seen this before, a popular common difference whose occurrence is roughly at least as much as the random case. So Ben Green showed the following popular difference for Roth's theorem that, okay, so let me put it this way. If you have a set A, a subset of interval 1 through n, then there always exists some popular common difference D, such that the number of 3APs in A with common difference D, with the specific one common difference, is at least this quantity here. Just notice a typo, there should not be a square. So this should be just alpha squared minus epsilon times n. In fact, I think I make this mistake many times in this talk, so I'll apologize for that. So there should be just n over here. Green's theorem is proved via so he developed a new arithmetic analog of Semirati's regularity lemma that works for the arithmetic setting. So instead of partitioning a graph into vertex sets where the graphs between vertex sets are pseudo-random, he developed an analog of such a tool for the arithmetic setting that respects the underlying arithmetic structure. And this became also a powerful tool for many other applications. Okay, so there's Green's theorem once again with the caveat that there should not be a 2 over here. So I want to lead on several questions that one can explore further with this popular difference theorem in two different directions. One is quantitative. How large does this n naught have to be? So Green's theorem uses the arithmetic regularity lemma that he developed, and the arithmetic regularity lemma, similar to Semirati's graph regularity lemma, needs a dependence, a quantitative dependence, which is quite terrible in terms of the dependence on epsilon. essentially you need something that grows as a tower of exponentials in height polynomial in 1 over epsilon. And it is known that for the arithmetic regularity lemma itself, this dependence is tight. Right? So this is known for the graph case due to Gowers, and in the arithmetic case, so Green already showed a slightly weaker version of the result, and then this full polynomial tower dependency was shown in this later paper. One result that I would like to present today is in joint work with Jacob Fox and Hui Pham, that the optimal N naught in Green's theorem is actually a tower of exponentials of height on the order of log 1 over epsilon. And so there's a new upper bound and a lower bound to this statement. Earlier result by Fox and Pham established the same type of result, but for the finite field setting. Instead of working in the integers in interval 1 through n, the finite field setting, one works in, let's say, f2 to the n or f3 to the n for a fixed p, fp to the n. A significance of this result is that it is the first application of the regularity method of Semmelweis regularity method, this important method and philosophy in extremal combinatorics, where we demonstrate that the tower type bounds are necessary. So just to elaborate on that a little bit further, Semmelweis developed his regularity method and proved lots of fantastic applications. And to this date, there are still many applications, such as the triangle removal lemma, where a regularity type proof is the only one that is known. But for many applications of the regularity method, there are now newer proofs that avoid completely the use of regularity method and give reasonable bounds that do not involve any function that's a tower of exponentials. But it remains, it remains an interesting question whether every use of the regularity method can be, in some sense, eliminated. And this example shows quantitatively that, in some sense, the answer is no, that this application, right, so Green's application, which is not, so on one hand, the regularity method itself is known to have tower type bounds, but for an application such as this consequence to Roth's theorem with popular differences, we show that the tower type dependence on the parameters is indeed necessary. The second direction I would like to explore in this talk is more qualitative, concerning what patterns other than 3APs can you have this type of popular difference result. Okay, so was there some issue with, do I still have the screen sharing on?
It looks like you're not showing your slide anymore.
It says host disabled attendee screen sharing. Maybe can you make me a co-host? There were some.
Sure, don't know why that's happened, but 1 second. Okay, you're a co-host now.
Okay, great. Let me try again. Okay, are we back on?
Yeah, you're good. Okay. Sorry about that.
No worries. So the second direction I would like to explore today is, what about patterns other than 3-term arithmetic progressions? Right, so what can you say about these other, well, instead of 3-term APs, what about other patterns like other KAPs or other multidimensional patterns? Is there also a popular difference type theorem? Right, so Ryan asked in the chat, what do I mean by application? The regularity lemma itself is an application. Well, so I don't consider the regularity lemma itself to be an application in what I just said. So I mean natural, combinatorial, extremal combinatorial consequences that you can state and will be interested in, whose statement does not involve the regularity lemma itself. A natural extension of the Roth theorem with popular differences would be that for 4APs. So Semmelweis 4AP theorem is also true with this popular difference consequence. Again, with the caveat, there should not be a 2 over here. So this due to a lot of copy and pasting. Sorry about that. So there So it's the same statement, except instead of for 3 APs, we have it for 4 APs. You can guarantee a common difference that has a lot of 4 APs, at least as much as roughly random. So this proof uses quadratic Fourier analysis. And at this point, you might suspect that, well, we know how to prove for 4 APs that uses quadratic Fourier analysis, and we have higher order Fourier analysis, so maybe the same result should be true for KAPs for OK. But in fact, that's actually not true. So surprisingly, it is known that such a statement is completely false for 5 APs and longer. Okay, so this was shown in an earlier paper of Burgos and Holst and Kra with an appendix by Ruja. So in there was a construction of a set with no popular difference for 5 APs. In fact, they put forward this conjecture, this general question about popular differences, would attribute that question to this Burgos and Holst, Kra, Ruja paper. What about other patterns? So instead of 5 APs, what about, let's say I give you an arbitrary 4-point configuration. Instead of 4 APs, which are dilations of 0, 1, 2, 3, what about dilations of 0, 1, 2, 4, or name 4 other numbers that you like? Is there a popular common difference type result for 4 arbitrary points? What about higher dimensions? So the first basic case of higher dimensions would be that of something called corners. So in Z squared, 3 points forming this right isosceles triangle with axis aligned legs would be called a corner. Okay, is there a popular difference type result for corners? Note that if we go up to higher dimensions for any pattern other than corners or 3-point patterns in 2 dimensions, we actually do not have a higher order Fourier theory for such patterns. And there are significant obstacles, as demonstrated by Tim Austin, that prevents us from, I mean, currently we just don't know how to do any higher order Fourier analysis. So that's something that's maybe worth keeping in mind, and I'll address this a little bit towards the end as well. So let me state this question more precisely. For which finite sets P, let me call that a pattern, so P should have at least 3 points. It turns out for 2 points, the situation is rather easy, and the answer is always yes, but 3 now has always at least 3 points, have the following property. For every set A of n to the r, there exists some popular difference D such that A contains at least as many as roughly random translates of some fixed dilation, this D, a single D times P. Okay, so that's a popular common difference. I want A to contain many translates of this P under dilation by this popular common difference. Here, alpha is the density of A in the ambient set. Green's proof, previously I stated it for 3 APs, but actually the proof works equally well for all 3-point patterns. For 4 APs, so that was proved by Green Tao, and their proof actually shows that any 4-point pattern of the form 0, A, B, A plus B, so a 2-dimensional parallelepiped in 1 dimension, is also has this popular difference property. Okay, so are there any other patterns with this popular difference property? So we show that the answer is no, but these are all the patterns. No other patterns have this popular difference property. Given that, okay, I'll explain more our theorem, but given that, you can also ask the next quantitative question. For a given pattern, what is the optimal parameter you can put here? What is the optimal popular difference density? Can you guarantee that every set A must contain? So let me now explain Green's proof, give a high-level overview of Green's proof of Roth's theorem with popular difference. And I'll illustrate it here in the somewhat easier finite field setting, f3 to the n. More generally, you should use Bohr sets instead of subspaces, as usual in additive combinatorics. Let A be a subset of G. G is this f3 to the n, and f be the indicator function of A. Green proves an analog of the graph regularity lemma. So this arithmetic regularity lemma, very informally says that you can find a subspace H with bounded codimension, in this case, this bound is of tower height, such that f sub H, which is defined to be the function obtained by taking f and averaging the f values of f along each H coset. Okay, so it also can be equivalently written as a convolution of f with a probability measure, uniform probability measure on H. So the regularity lemma says that f sub H approximates f really, really well. So there's some quantitative dependence here in terms of Fourier uniformity that I will not state precisely here. Let's denote the 3AP density with common difference in H by this expression, this quantity here, lambda sub H of f. So unlike the 3AP, three-term arithmetic progression density, what I've written here is 3AP density with restricted common difference. The common difference is restricted to be within H. So you're only allowed to take jumps Y that lie in the subspace H. With a regularity lemma, it comes with a counting lemma. And the counting lemma says that the 3AP density with common difference restricted to H is roughly at least as much as, I mean, it's roughly the same as, but certainly at least as much as the 3AP density with common difference in H. But instead of F, now we look at the approximation F sub H. So in general, a counting lemma is some result of the form. If you have some regularity approximation, then some statistic are similar between the original function and the approximation. So in this case, the counting lemma tells you something about restricted 3AP counts. But f sub H is constant along cosets of H. And in particular, for every y in H, these three factors in this expression here are all equal to each other. So this lambda sub H of f sub H is actually just the third moment of f sub H, okay, and which is at least the density of f cubed. So it tells you that if you take a 3AP, so the density of 3APs with common difference in H is roughly as much as what you expect in a random case. And in particular, provided that H is not too small, one can find a popular common difference in H. I need this provided H is not too small, because if H were, let's say, just the origin, a single point, then you wouldn't be able to get a non-zero common difference. Okay, job asked it, so that's right. So there's a typo. I'm sorry, there's another typo. So the average should also be over X in the vector space. So X in the vector space and Y in H. Thank you. Okay, so this proof works provided that H is not too small, and combined with the regularity lemma, it tells us that the proof works provided that N is big enough, and big enough is at least tower height in polynomial in 1 over epsilon. Let me discuss okay, so what we do now as that gives you an improvement, a tower log improvement in Green's theorem. So instead of using a energy increment argument to prove the regularity lemma, we use a different type of energy, a cubic energy. Okay, so meaning just the third moment of F. A regularity lemma that is specifically tailored for this application tells us that there exists a pair of subspaces, W and U. And this pair of subspaces, this type of setup should be familiar to anyone who's seen things under the name strong regularity. Okay, so but otherwise don't worry too much about it. And such that on one hand, F is well approximated by F sub W, so F averaged over W cosets. And on the other hand, you have something like this, which is kind of an energy increment type statement, except with cubic energy. And there's this extra factor of 2 that you don't normally see. And what this extra factor of 2 roughly translates into is that in the usual proof of the regularity lemma, where the energy, the usual energy, the L2 energy, goes up by, let's say, epsilon each iteration, we actually get a lot more in this new regularity lemma. The energy roughly doubles at each iteration in the regularity proof. And as a result, instead of poly 1 over epsilon iterations, you have log 1 over epsilon iterations. Okay, so that's where the gain comes from. Why such a energy, cubic energy is useful? It turns out we use the following classical inequality due to Schur. This is one of those things where if you did math competitions, math Olympiads, then you should probably remember such an inequality. It was very useful back in the day. Okay, so you have this inequality for non-negative real numbers A, B, and C. And plugging this inequality into the expression for 3AP densities, with A, B, and C being the 3 factors that come up over here, one deduces an inequality for 3APs with restricted common differences. And as a result, we get a different type of counting lemma that is, so the regularity lemma is tailored to produce this counting lemma that tells us that the 3AP density with common difference restricted into the subspace U is at least as much as random. So provided that U is not too small, we can deduce that U contains some popular common difference. And this proof works provided that N is not too small, and because of the slight gain in the parameters in the regularity lemma, we get power of constant times log 1 over epsilon. For the lower bound, showing that this powered log is tight, so let me sketch a few ideas that are involved. So first, Gowers showed this in this very important work that tower type bounds are indeed necessary for Semiramis graph regularity lemma. And the proof of Gowers uses a certain iterative construction. It's in some sense reverse engineering the Semiramis graph regularity proof, showing that each step of the proof has to be forced. It's necessary in this iterative energy increment proof. So our result, which gives you a construction of a set without 3AP common difference, follows a similar type of iterative construction idea. And the construction in the very broad strokes goes like this. We take a sequence of increasing primes, so there are some parameters on how quickly these primes should be increasing, and we construct weighted functions step at a time, one step at a time, starting with some carefully designed F1, and then extending that F1 to F2, and then adding some random modifications to F2. And further on, tacking on extra prime factors until we get a function on this product of cyclic groups, which is again a cyclic group. And each step of the way, we maintain that F sub I has the 3AP popular, so each has no 3AP popular difference. So maintain the property that each F sub I has no popular 3AP common difference. Finally, to convert this last step construction, we finish by, let me just call this a barren twist, so adding something related to the barren construction to get it for the full cyclic group. Okay. But the main message I want you to take away is that it's an iterative construction similar to what Gowers did. We do this one step at a time, and each step maintaining the no popular common difference property. And this is done through a combination of extensions and random modifications. Let me now move on to questions about other patterns. Okay, corners. So given a subset of n squared and of density alpha, is there always some non-zero d such that there are at least, I notice that there should be actually n squared, so not n cubed, sorry about that. So alpha cubed minus total 1 times n squared corners with this popular common difference. Okay, so it's the same kind of question. Is there always some popular common difference whose occurrence is at least roughly as much as random? Here, little o1 goes to 0 as n goes to infinity should not depend on alpha. So Matai and Denshi showed that the answer is no by constructing a set A with alpha to the 3.13 n squared corners for every common difference. Okay, so this alpha cubed is, so this statement over here, the answer is no. You do not have popular difference for corners. On the other hand, Mendashi also showed that so in the positive direction, you can find some common difference D with at least roughly alpha cubed and so n squared, sorry, alpha to the 4th n squared corners. So while the answer is not 3, if you replace this number 3 by 4, then the answer should be yes. Okay, so the answer somewhere lies between this 3.13 and 4. Right, so what should be the popular common difference density? So Mendashi proved this result for the finite field setting f2 to the n, and using a similar framework, but now using the Bohr-set machinery, the same result was extended to all abelian groups as well as intervals in the lattice, integer lattice, by Aaron Berger, who is my student at MIT. Mendashi reduces the popular difference for corners problem to a certain variational problem, which I'll describe in more detail in the next couple of slides. The upper bound construction showing that the variational problem implies an upper bound on this popular common difference density goes via a probabilistic construction. And that's what he used to construct this no example. Whereas the lower bound uses an arithmetic regularity type argument, but for corners instead of for 3 APs. Just a little bit of background to that. For higher dimensional, so multi-dimensional similarity theorem, in general, we do not know a Fourier analytic proof, and that's a major open problem. The only known proofs for multi-dimensional similarity theorem, or the first original proof, was via ergodic theory. And then later on, there was this important breakthrough that part of this polymath project, sorry, not poly, so due to, confusing myself. So there's a theorem by Gowers and separately Roth and co-authors that gives a hypergraph regularity type tool, which gives you a hypergraph removal lemma that also implies multidimensional similarity theorem. But in general, we do not have Fourier analytic approaches to higher dimensional similarity theorem, except in one specific case, namely that of corners, or 3-point patterns in 2 dimensions. And that's due to Skretov. And this type of method was incorporated in Mendashi's work to give an arithmetic regularity type result for corners. Okay, so I want to discuss some new results that sharpened bounds on what should be the popular common difference density. And we show that the optimal parameter you can put in here is, on one hand, strictly asymptotically greater than alpha to the 4th. So omega, so meaning asymptotically strictly greater than alpha. So omega is like the opposite of little o. Right? So it's strictly greater than alpha to the 4th, where the 4 in the exponent is best possible. So I left out strictly what are the hidden parameters, but there is still a gap, and you'll see where the gap comes from in a couple of slides. I want to explain what is the variational problem that Mendashi reduces the problem to. And it has a certain very attractive form. So it involves a certain hypergraph, a 3 uniform hypergraph. It's an extremal problem on a 3 uniform hypergraph. This 3 uniform hypergraph, we found a very nice name for it, and it comes up in this popular video game, Legend of Zelda from Nintendo, and it comes up as a hallmark, an icon in this video game. Okay. There it is called a Triforce. So that's what we're going to call it. It's the Triforce. The Triforce is a 3 uniform hypergraph on 6 vertices with 3 edges, so 3 triples. Okay, I hope that this name sticks. If you see this hypergraph come up in your work, call it the Triforce. So Mendashi, for finite field setting and later extended by Berger to integers and abelian groups, reduces the popular difference problem for corners to the following extremal problem for Triforce, namely to find the maximum Triforce density in a 3 uniform hypergraph with given triple density. So triple density means edge density. Okay, so we show that this maximum Triforce density, G of alpha, is strictly between alpha to the 4th, asymptotically greater than alpha to the 4th, and the 4 is optimal up to a little 1 additive in the exponent. The lower bound comes from application of triangle removal lemma. So previously Mendashi showed alpha to the 4th power, and we managed to give an extra boost on top of that with the help of triangle removal lemma. And the upper bound comes from a barren construction using 3AP free sets related to what's known as a Ruja-Semirati graph. And more generally, instead of a triforce, you can talk about a k-force for k at least 3 instead of a empty triangle surrounded by a bunch of triples. Let's say the 4-force would be an empty tetrahedron and attach a tetrahedron to each of the faces of the middle missing tetrahedron. So the maximum k-force density in a k-uniform hypergraph is between these 2 quantities, so generalization, the straightforward generalization of this theorem up here. I want to mention a related problem, which is somewhat similar in theme, slightly easier, but similar in theme. So I learned of this problem from Tao's block, Terry Tao's block, which is if you are given a graph, if you know that a graph, so a 2 uniform, a graph has triangle density beta, what can you say about the maximum possible diamond density? The diamond is this object over here. And it is known that it is between, strictly asymptotically greater than beta squared, but this 2, actually this 2 is optimal in the exponent. Okay, and here the beta, so the lower bound also uses the triangle removal lemma, and the upper bound comes from a similar barren construction. So here you have a log star type quantity in this lower bound. So let me move on to higher dimensional corners. So given that I said that, so Aaron asked what about max? Okay, so maybe I messed up on max versus min. Yes, so I think this should be, sorry, that should be minimum triangle, minimum diamond density. Yeah. So given I said that the Triforce theorem generalizes to higher uniformity hypergraphs, you might suspect that the similar consequence for corners also extends. But actually that's not what I said, because the reason that the Triforce implies the popular corners theorem is that there was this arithmetic regularity due to squared off 4 corners, and we don't have such an arithmetic regularity for higher dimensional corners. So the generalization to higher dimensional corners actually does not hold, and in fact it is false. So there is no popular difference for 3-dimensional corners. For every alpha, there exists, we can construct some A such that A has density at least alpha, but the number of 3-dimensional corners, I keep making this mistake, should be n cubed. So the number of 3-dimensional corners with common difference d is super polynomially small as a function of alpha times n cubed for every non-zero difference d. So in other words, there exists A such that there are no popular differences in a very strict super polynomial sense, in sharp contrast to 2-dimensional corners. Let me show you a quick sketch of the proof. The idea is to stack a barren construction. So originally we gave a more involved proof in this paper, and a simpler proof was found recently in a different paper with Ashwin Sa and Mehtab Soni. So you take a set B with very few corners. So there exists a set B, a subset of n squared or z mod nz squared with very few corners, and it's a derivative of the barren construction for sets with few 3APs. And let us layer and stack layers of B. So here we're working in z mod n cube. Okay, so stack layers of B, where each layer I take a dilation of B. So 2 times every element of B, 3 times every element of B, and so on. You stack these layers together. Now note that the density of 3-dimensional corners, so the pattern up here in this stack, we can even just forget about one of the corner points. Let's forget about this red point up here. So the density of 3-dimensional corners is at most the density of 2-dimensional corners in anywhere throughout the stack. But the density of 2-dimensional corners in this stack is the same even with a fixed common difference. With a fixed common difference, the density of 2-dimensional corners with a fixed common difference in the stack is equal to the density of 2-dimensional corners in B, in a single layer, without any restriction on the common difference. Because when you go up the layers, I'm changing the common difference. But B has very few 2-dimensional corners. And as a result, this whole stack has very few 3-dimensional corners with any fixed common difference. More generally, this construction of stacking a barren type construction, stacking a single construction with very few corners or some patterns, shows more generally that if you have a pattern which has 3 points that do not span the whole space, so in this case I have 3 points that span a 2-dimensional space, whereas we're in a 3-dimensional pattern, then there exists a construction obtained by stacking where you do not have any popular common difference in a super polynomial sense. Let us now go back to 1 dimensions. I mentioned earlier that a result of Bergelsen, Host, and Kra with appendix by Ruja showed that there's no popular difference property for 5 APs, in sharp contrast to 3 AP and 4 AP, where there is a popular difference theorem. In this paper with Fox, Soni, and Stoner, we note that the argument of Ruja can be extended to all 5-point patterns, not just 5 APs. So for every 5-point pattern, so this statement here is for 5 APs, but if you replace the 5 AP by any 5-point pattern, then the popular difference density, you can choose some set A such that the popular difference density is super polynomially small in alpha. I won't be able to describe the whole construction, but let me give you a sense of what some of the ideas involved. In particular, I at least try to explain maybe in a numerology sense of way where this number 5 comes from. Recall that Behrend constructed a 3AP free subset of 1 through L of size this much, obtained by as the image of a projection of a set of lattice points of some higher dimensional sphere. So you take some high dimensional sphere, take all the lattice points on it, so you pick a sphere with lots of lattice points, and a sphere has the nice property that the sphere itself contains no 3 points on a line, and in particular has no 3 APs. And that's a really useful property, and if you project that sphere onto one dimensions appropriately, then you maintain this property of containing no 3 AP. Okay, so why 5? Why 5-point patterns in one dimension? Why is there no popular difference? What is this construction of Burgos and Host-Croix and Ruja? So the idea is supplied mostly in this appendix by Ruja. Okay, so where does that come from? So it's related to Behrend, but there's an extra twist on it. And the 5 comes from the following fact, that a quadratic curve intersects a sphere in at most 4 points. So whereas a line intersects a sphere in at most 2 points, a quadratic curve intersects a sphere in at most 4 points. So this Behrend construction, basically the same construction, can be twisted into a quadratic Behrend type construction, that there exists a subset of 1 through L of size same as Behrend that does not contain any pattern of this form. So 5 points that are part of a quadratic progression. So P0, P1, P2, P3, P4, P4 for some non-constant quadratic polynomial P. Right? If P were a linear polynomial, then this would be a 5AP, but here I require a quadratic polynomial. Okay, and that's related to not having 5 points on the intersection of a quadratic curve and a sphere. Okay. And at this point, you probably don't see why it's related to 5AP popular common difference, and I won't have time to explain that, but this is all I will say about this construction, and you can use this construction then with extra steps to do what Ruja did. Let's go to 4-point patterns in one dimensions. So one of the positive results I mentioned early on was this result of Green and Tao, showing that there is a popular difference property for 4 APs, and it involves not just quadratic Fourier analysis, because so quadratic, if you only involve quadratic Fourier analysis, then somehow you would expect the same to be true for every KAP. But there's something extra about 4 APs, and namely that there's a certain positivity, and almost a coincidental positivity that comes in the proof. And this is reflected in the following fact, that if you look at these quadratic forms, x squared, x plus y squared, x plus 2y squared, x plus 3y squared, which are quantities that come up very naturally in the quadratic Fourier analysis of 4 APs, then the only linear relations between these 4 quadratic forms is this linear relation. And it just happens that it looks symmetric. It has symmetric coefficients. Right? So this 3 is the same as that 3, and this 1 is the same as that 1. And this symmetry plays a key role in this popular difference proof, in that one of the terms in this analysis is non-negative as a result of this symmetry. So you can extend the same argument to any 4-term patterns of the form 0, A, B, A plus B, because instead of 2 and 3 and 1, if you replace it by these 4 numbers, then you would obtain a similar symmetry between the coefficients. So you can ask, well, what about other 4-point patterns that do not have this symmetry property? So without this symmetry property, such as 0, 1, 2, 4, if you write down, so you can write down a linear relation between the quadratic forms, and we'll see that in a second, but they no longer have symmetric coefficients. And in this case, do you also have popular difference? The proof no longer works. And in fact, the result, okay, so it's, so that's the question. So the proof no longer works. The Green-Tao proof no longer gives you popular difference for 0, 1, 2 form. And in fact, for good reason, because it's not true. So we show that provided that you are not one of the patterns that can be handled by the Green-Tao proof, there is no popular difference in the following sense. You can find some A where the number of four-term patterns for any fixed, let's still call this a popular common difference, Y, is no more than 1 minus some absolute constant C times the random bound. Let's say 0.999 times random. Okay, so not quite strictly as much as random, not as, this is not as strong of a result as the Barron type constructions that we saw in earlier slide, but it shows you at least that this random, the more naive random guess is incorrect. Now, let me sketch some of the ideas that go into this theorem. And I should mention, I'll also say this at the end, that it remains an open question to improve this bound and also to find some reasonable lower bound. In pretty much all the cases that I mentioned, except for the 4 situations, Green's 3-point pattern, Green-Tao's 4-point pattern, and Mandashi's corners pattern, where there is Fourier analysis available. In all the other situations where there's no Fourier analysis available, we basically don't have any lower bound to such theorems other than the ones that come from multidimensional similarity theorem itself. Namely, so for the multi-dimensions, for using multidimensional similarity theorem, and for 1 dimensions using similarities theorem. Whatever bounds you get for similarities theorem, you can deduce a bound for popular difference just by averaging. And in general, we don't know how to do better than that for lower bound. So there's a big gap to be closed between the lower and upper bounds. So let me illustrate the idea that goes into a construction of a set without popular difference for a 4-point pattern. And let me start with the pattern 0, 1, 2, 5. Okay, why not 4? I'll explain that in a second, but let's start with 0, 1, 2, 5. The construction, so we wish to construct a function, which is, think of it as a weighted set. We wish to construct a function with density at least alpha, such that for every difference y, this form, right, so this quantity, which is the weighted analog of the pattern density for the 0, 1, 2, 5 pattern, is no more than 0.999 alpha to the 4. Okay. And so as Ryan points out in the comments, what we do at the end is we sample F to obtain a genuine set A by taking each element X with probability F of X. The construction of such a function F is as follows. So this is a kind of thing that comes up quite naturally in quadratic Fourier analysis, is to consider functions that whose constituents are these quadratic exponentials. Okay, so this is a function that we're going to construct. I normalize F by alpha for convenience, and the terms are displayed over here. And you see some numbers that come up in exponents 6, 15, 10, and 1. And those numbers are chosen for a good reason, because these are the numbers that come up as coefficients in the non-trivial linear relation among the quadratic exponentials. Okay, so among these quadratic forms that come up naturally for this pattern, 0, 1, 2, 5, this is the linear governing relation. With this construction here, by a routine calculation using Gauss sum cancellations, you can deduce that F has density around alpha, and the analog of 4AP density, but for the 0, 1, 2, 5 pattern in F, is this quantity over here. You have this main term alpha to the 4th, and then this extra term which come from some coefficients attached to these quadratic exponentials. And so this is some calculation you can do, and the point is that everything else cancels due to Gauss sums. So here is, okay, so note that here I only average over X. I do not average over Y. That is really important for every fixed non-zero Y. this is true. And that will be an important difference between 0, 1, 2, 5 and 0, 1, 2, 4, which I'll show you on the next slide. So now, well, with this expression at hand, you just pick the appropriate values of gammas. Let's say you can pick a small negative value for gamma 1 and a bunch of small positive values for gamma 2, 3, 4. And that would give you a slight depression from alpha to the 4th power. And that's what you want. Now, what about 0, 1, 2, 4? Okay, so why did I not do this example immediately? So we follow the same scheme. So we follow the same scheme. We wish to construct a function with this property over here. And you write down this expression, then the appropriate coefficients, if you follow the same scheme, are these numbers 3, 8, 6, and 1. And they're chosen because there's a very similar linear relation governing quadratic forms. So those are definitely the numbers that you want to put in, at least following this framework. But now if you expand this expression corresponding to pattern density of 0, 1, 2, 4, and average only over x, but not y. So for every non-zero y, this d should be a y. I apologize. This d should be a y. All of these should be y's. You get this expression over here, where you have not just the terms that we've seen before, but some extra terms that involve only the numbers y. That involve only the numbers y. Okay, so the d should be a y. And the extra terms are due to additional linear relations among the quadratic exponentials. You have some extra linear relations not seen for the previous pattern, where I have this linear relation on the right-hand side. I have some quantity that depends not on x, but only on y. And these extra relations they need to be handled because we want to find a construction that works for every y. Now, fortunately, in this specific example, 0, 1, 2, 4, we're still in a good situation. I mean, this expression here, if you pick, again, a small negative gamma 1 and a bunch of small negative, positive gamma 2, 3, 4, this expression is still strictly less than 1 inside the parenthesis, so you're still okay. But it should give you a warning sign that for general patterns, you need to think about what kind of garbage can come up in these as a result of extra linear relations between quadratic forms. And they all need to be either eliminated or handled. And they can come up in very subtle ways. So for our general theorem, we need to rule out all such linear relations. And our proof, unfortunately, uses a computer-assisted proof. So we search for all possible linear relations that can come up between these quadratic exponential forms and so between these quadratic forms. And the proof itself uses lots of computer searches as well as various subroutines concerning finding rational points on hyperelliptic curves. But the final result is that of 4-point patterns in 1 dimensions for every alpha between 1 and 0 and 1/2. There exists some set A with no popular difference in the sense of 1 minus absolute constant times random. For certain patterns, we can do much better. Right? So you might not be so happy with this 0.9999 alpha to the 4th. And unfortunately, in general, that's more or less the best we can do for a general pattern. But for certain specific patterns, we can do much better. Namely that for every constant c there exists. So you give me a c, let's say 1,000,000, then I can spit out for you a pattern, a 4-point pattern, where the right-hand side can be replaced by alpha to the 1,000,000. So unfortunately, we don't have any example where the right-hand side can be replaced by something that is super polynomial in alpha. That remains an open question. Okay, so the question is, does C depend not on the A1, 2, 3? Actually, in our proof, the C is an absolute constant. It does not depend on the choices of the 4-point pattern. Although in general, so in this case, the C does not depend on the 4-point pattern. For some of the results I mentioned earlier, there was C in the exponent in Barron's, something related to Barron's construction. There, the C may depend on the pattern. But here, the C for 4-point patterns in 1 dimension is an absolute constant. This construction, I just want to point out, and I won't have time to go into more explanations, but it is related to a notorious open problem of the following, the specific problem, but also general problems of this type, that what is the maximum size of a subset of 1 through n, avoiding the following equation: x plus 3y equal to 2z plus 2w. Okay, so Rusha asked this. This is it's a famous open problem, and the best that we know is that it's somewhere between root n and little o of n. And even if you change this equation to change the 4 coefficients, but still keep 2 positive coefficients on one side and 2 positive coefficients on the other side, and still make a translation invariant, we don't have anything which is like a Barron type construction. So there's always a polynomial gap between the upper and lower bounds. I mean, the upper bound is always little o of n. We don't know if the exponent 1 is tight, and the lower bound is something which is n to some other power. Sometimes it can be bigger than 1/2, but in general, it's an open question to close the gap. And this type of example is related to these constructions up there. I want to mention a somewhat tangentially related question of Gowers. So to give a little bit of background, the basic idea of the Fourier analytic proof of Roth's theorem is that if you give me a Fourier uniform subset of Z mod n with density alpha, then a counting lemma tells you that it has 3AP density around alpha cube. And unfortunately, this, or fortunately, depending on how you see it, this statement is false for 4APs. But the standard example showing that it is false for 4APs is this example, which is related to the quadratic exponentials I've shown earlier. But this example, I mean, this is the standard example showing the counting lemma fails for Fourier uniform sets for 4APs, but it actually has more 4APs than expected. So if you run the Roth proof for 4APs, what might cause problems is a Fourier uniform set with too few 4APs. But this example is not actually a counterexample to that to that difficulty. So it's not an obstruction to the density increment argument. So far in principle, we don't actually have something concrete that says that Roth's proof does not work for 4APs. Right? So it could be in principle that you can still run Roth's proof for 4APs. We don't expect that to be the case, but we don't have a concrete example showing that that cannot be done. So what I'm asking, or rather what Gowers asked is there a Fourier uniform set with 4AP density much less than alpha to the 4th? And he indeed constructed such an example. So he constructed this some time ago, but he only recently put up the preprint on the archive. So Gowers constructed such an example for AP with density less than random, but only slightly less than random. And he asks, is it the case that a Fourier uniform set of density alpha has necessarily 4AP density at least alpha to some fixed power, let's say 1000? It's somewhat related to the theme to the kind of questions I discuss in this talk, although it's not about popular differences. Okay, so we don't know. I mean, we don't make any progress on this problem. I think it's a very interesting problem. I just want to point out that the result that I showed you on the previous slide implies that if you change the word 4AP to an arbitrary 4-point pattern, then, well, the statement as written, the answer is no. Maybe if you're allowed to change the number 1000, the answer might be yes, but even that is, well, we don't know. So it's an interesting question. Okay, so the last result I just want to briefly summarize for, I described, this talk may seem like a laundry list of different patterns, but each one I think is interesting on its own. And the remaining case, so I've pretty much covered all the cases out there, but the remaining case is what about 4-point patterns in 2 dimensions? And so for every 4-point pattern in 2 dimensions, the answer is the following, or at least what we can prove is the following. If you have a convex pattern, 4 points in convex position, then the number of translates, okay, so keep making this mistake because I think of the total number of patterns, but actually you should be only thinking of patterns with a fixed common difference. So this 3 should be a 2. So the number of translates of y times p is at most roughly alpha to the 5th power. So this is alpha to the 5 plus little o 1. So no popular difference, but only slightly in the exponent. So instead of alpha to the 4th, we prove an upper bound of alpha to the 5. Whereas for a non-convex 4-point pattern, the upper bound can be substantially improved to barren type. And I won't have time to tell you what it is. I'm already running a bit over in time, but just to mention that for non-convex patterns, you could think of this construction as related to that a sphere in high dimensions has no 4 points in non-convex position. Although it's a little bit more subtle than that. We actually use a certain complex number twist on the barren construction. Okay, so the final summary slide. So let me just go over all the results I've discussed today. So the starting point of everything is this popular difference for Roth's theorem due to green. So one of the things I discussed is quantitative aspects, namely that is n sub n naught of epsilon, how large n needs to be in Green's theorem. We determine the optimal parameter, we determine the optimal n, which is on the order of tower of height on the order of log 1 over epsilon. And this is the first application of the regularity lemma where the tower type dependence is necessary. And here's a table summarizing various different types of patterns and bounds that we can prove for popular difference density. So this quantity here is basically what's the best number that you can put in place of the random bound in the popular difference theorem. Okay, so we prove various bounds. And in all these cases, I mean, you see a bunch of barren type bounds, but there are a couple of places I want to point out where we actually have a pretty big gap between upper and lower bounds. I mean, I didn't state the lower bound, but essentially comes from Semiretti's theorem. And the upper bound is a small improvement on the random bound. And I will leave these two as the main open problems to improve both upper and lower bounds for these two patterns here, namely for 4-point patterns in 1 dimension and for 4-point patterns in convex positions in 2 dimensions. Okay, and that's it. Thank you.
Thank you, Yufei, for a very lucid talk. Let's all try unmuting and clapping. Are there any questions?
I have a question.
Hmm?
Yeah.
Do you have a guess about, or some idea about when the bound should be polynomial in alpha?
Right, so when should the bound be polynomial in alpha? Yeah, so the only 2 missing cases where we don't know is these 2 highlighted cases. And yeah, that's a great question. I'm not sure if I want to make a guess. I mean, depending on which day you ask me, I might go either way. So maybe they look more like these barren type upper bounds, or maybe there is some, yeah, I don't know. I really don't know. For 4-point, okay, I can tell you almost definitely that even if there were a polynomial type lower bound for 4-point patterns in strict convex position, actually in this case, a good example to fix is axis aligned geometric square. And so 4 points in axis aligned geometric square. It seems really difficult to do that because all the other techniques that we've seen so far, you need some kind of Fourier analysis, and we just do not have a Fourier analysis that can handle that pattern for Semiretti's theorem. But it may well be the case that there might be a polynomial type lower bound in this case. Or maybe there's a barren type upper bound, I just don't know.
I have a question about, so you used the Baron construction several times. In all these cases, do you just care that this is a large set without three APs, or do you actually care about the details of the Baron set? So if someone came out with some super cool construction of an even bigger set without three APs, would that be automatically useful to you?
Yeah, it's a good question. So in all of the cases of the Baron construction, we, okay, the answer is yes and no. So on one hand, in all of these applications, when I say Baron, instead of three APs, you need to adapt it to a specific pattern, but it's basically the same construction. So Baron, you can modify Baron for other patterns that are related to three APs. There is one case, namely, well, I mean, actually, there are some cases here where you need, okay. So in Rouget's construction, right? So in Rouget's construction, he uses not just Baron, but actually some of the ideas that come from Baron. So I mentioned there was a slide of a quadratic curve intersecting a sphere in at most 4 points. Right? So that's like going into Baron's construction. There you actually want to know that Baron's construction comes from a sphere. So it's not just Baron as a black box. At least in that construction, you want to know like how Baron constructed his 3AP free set. Yeah, but in some of the other constructions, you know, one slide was stacking Baron, and there you just need as a black box some set with very few patterns.
Mm-hmm.
So I have a question.
Yeah.
Yufei, have you looked at polynomial progressions?
Okay. Yeah, so polynomial progressions, so no, we have not looked at polynomial progressions. I think it's a great question, and there are, yeah, so you have to figure out what is the right question to ask, because there are several different variations depending on whether you're working in Z mod n or you're working in 1 through n, in which case you have to adjust the length. But I think that's, we have not looked at polynomial progressions.
Wait, how about progressions where like, okay, how about you take 4 points, but they're not dilates and translates of any fixed set, but like maybe, you take P is a 1 mod 4 prime, you take like the 4 roots of the 4 things whose fourth power is 1 or something. You look at translates and dilates of that, or some other set that sort of grows with P. That's not like a globe of a small.
Yeah, so in this talk, I only discuss patterns that come from dilations and translations. So certainly you can come up with other, let's say, 1 parameter families of patterns.
But so patterns that come from dilations and translations of a set, but it's not like a fixed size set, but that maybe is a set that depends on P. Can you say anything about this, or do you?
Actually, I don't quite understand. What do you mean not a fixed size set? So you mean sometimes it's like 4 AP, sometimes it's a 5 AP, sometimes it's a 6 AP?
No. Okay, I mean like it's not a dilations and translations of a fixed subset of Z, but rather some sort of subset of Z whose like range grows with P or something like that.
So would a polynomial progression be an example of what you're discussing?
Yeah, but I think I want it to be closed under translations and dilations.
I see.
So,
I see.
Like, I take the 4 roots of x to the 4th is congruent to 1 mod P, and I take the closure of those under translations and dilations or something like that.
Okay, yeah, so we have not looked at any such patterns. Yeah, I don't have any thoughts about that at the moment.
I had another question, Yufei.
Yep.
So in your construction, so when you were looking at 4-point sets, you said you constructed this set that avoids 0, 1, 2, 4. It doesn't have any popular common difference for 0, 1, 2, 4. And you constructed another set which is the same for 0, 1, 2, 5, and you can do this for every 4-point set.
Yeah.
But should there be one set that's sort of universal for all these things? Should you be able to just have one construction that kills immediately all 4-point sets?
Should there be a universal pattern for all 4-point sets? I don't know. So in fact, so it's maybe slightly misleading that in these 2 slides for 0, 1, 2, 3 and 0, 1, 2, 4, the pattern I ended up taking, actually it's a different construction because you have different exponent over here, but I ended up choosing the same coefficients. And so even in general, in our construction, we needed to be more creative in choosing these coefficients, depending on what comes out of the analysis. But yeah, we don't know how to construct a universal set for 4 APs in general. Like our construction is tailored to any specific pattern according to the kind of obstructions that can come up in the quadratic Fourier analysis. And I think there could be very well a very different type of construction that will do much better quantitatively, not just a very tiny improvement on the random bound, but a more substantial improvement.
I see. By the way, in this slide, so the reason you can't take the gammas to be very large is just because you need this function to stay positive. Is that right?
Correct. That's
Yeah,
right.
okay.
Correct.
Are there any other questions? Well, if there are no other questions, let's all try unmuting and giving Yufei his second round of applause. Thanks, Yufei.